In this video, we present a supplementary overview of our paper, Manifold-Constrained MPPI, Real-Time Sampling-Based Control Under Hard Constraints. Let us first look at the framework overview. In this work, we consider real-time control of robotic systems subject to hard equality constraints. When an equality constraint is imposed, conventional MPPI struggles to handle it. As shown on the left, this is for two reasons. It suffers from sample inefficiency, since valid samples on the thin constraint manifold are rarely generated, and from weak constraint enforcement, since it relies solely on soft penalties that can never drive the violation to zero. To address this, we sample in a learned latent space through a VAA, which generates near-feasible samples directly on the constraint manifold. In addition, we introduce a two-stage architecture that handles the hard constraint directly, rather than relying on soft penalties. Our framework adopts a two-stage architecture. The first is the planning stage. In the learned latent space, we generate rollouts through the latent dynamics, decode them with the pre-trained decoder, and evaluate the cost in the configuration space. As a result, an optimal latent state is obtained, which is then decoded into a near-feasible reference configuration. However, since the VAE inevitably leaves a manifold mismatch, the reference does not lie exactly on the constraint manifold. To resolve this, we introduce the execution stage with a QP-based optimizer. It computes a feasible, optimal configuration that satisfies the hard constraint while still carrying out the task assigned by the MPPI planner. We now validate the proposed method through simulation experiments. In this tracking scenario, we command the tray to a target pose and compare the proposed MCMPPI against two baselines, latent MPPI and vanilla MPPI. Because vanilla MPPI samples directly in the configuration space and latent MPPI omits the execution level QP, both fail to maintain the constraint and break the grasp before reaching the target. In contrast, MCMPPI reliably preserves the equality constraint while converging to the target. This scenario covers obstacle avoidance while maintaining the manifold-based equality constraint. Here we also examine single-instance sampling, a technique from prior work that we simply adopt within our latent space formulation. With equation, a constant innovation is held over the horizon, producing smooth latent rollouts that explore deep along the manifold, so the variant quickly finds a collision-free path. Without it, per-step noise makes the latent velocity fluctuate. Amplified by the VAE decoder, this often manifests as jerky joint motion, and the variant suffers prolonged stagnation near the obstacles. We now validate the proposed method through real-world experiments. We validate MCMPPI in a real-world experiment. The results confirm that it can preserve the manifold-based equality constraint while avoiding obstacles in practice. This supports the practical applicability of the proposed method. We validate MCMPPI in a real-world experiment with a moving obstacle. The results confirm that it can preserve the manifold-based equality constraint while reactively avoiding the obstacle in real time. This supports the practical applicability of the proposed method. Thank you for your attention. Please see our project page for more information.